All right, guys, got a new section on the number e for you today. This kind of is like our last section where we had exponential functions and we graph those. Here, though, we're going to use e. So if you remember, we eventually had some word problems where we were to take like the interest and find kind of some simple interest and then maybe even compounded it. If you remember when we compounded, it was the equation, if I get my pen out here, of a equals p times 1 plus r over n raised to the nt, where this n, if this were to get bigger and bigger, right? Remember, it compounded quarterly, and that was a 4. We compounded daily, and it was 365. If you compound other numbers, right, it can become other things. But the bigger that this number gets, you might say that it approaches infinity. And if this approaches infinity, then this right here would be a really big number on the bottom. And so this would kind of, you could almost think of it as becoming a really small number. Anything divided by a really big number is going to be a really small number, if you think of it that way. But then raised to a really big number, well, a really small number raised to a big number, it almost nullifies a little bit. But the bigger this gets, as it approaches infinity, it's actually going to approach a whole number itself. And that's this section right here. And if you look at that, that is actually going to be the number e, which happens to be 2.7182, and so on. Okay, this is Euler's number. The way you pronounce this is Euler. He's a old mathematician. It's considered to be a natural exponent because it arises naturally in math and physical sciences. As that number approaches infinity, there are things that happen that way. Now, you might want to use a calculator to evaluate this. If you have a calculator like the ones we have in class, I have a TI-30, and underneath the second button is where the E is. So if I hit on mine, if I hit second E, it opens up a parentheses as it's raised to a power. And so if I were to type in E raised to the negative 2.3, this is going to give me a really small number, 0.100258. So I'll say maybe 3 if I round to 4 decimal places there. Whereas this one, if I take 125, E, and again, when I type in E, it just automatically raises to an exponent. If I go 0.0267, you might hear me type in here. This is going to be 128.3825, 0.3825, again, rounded a little bit on that last decimal spot. And then it says, how do you know if this is a growth or decay function? Well, we know that by whether the exponent is negative or positive. And if it's negative, if I have e raised to a negative number, this is going to represent an exponential decay. Whereas if it's a positive, like this one was a positive exponent, barely, right? It's still really small, but it is positive. That would be a growth. So anything e raised to a positive number is going to be an exponential growth. Oops. Helps if I spell it right, I guess. All right, so we're going to keep that in mind as we graph some of these in our next slide. And in fact, I left this one blank because I want to take you over to Desmos on their graphic calculator. And I already have this typed in for us. This is e raised to the x. This is if there's nothing around it. And you can see if we mess with this a little bit, if I were to put a number in front of this, let's maybe put a 2. Okay, you can see it goes up a little bit like that. In fact, if you remember back to our last section where it was a times b raised to the x, that first number is always 0a, and so that's still going to be true here. This would be 0.2. If I take that away, what number is in front of it now? Well, this should be a 1, right? If I put a 1 here, you'll notice it didn't move on me because this is the point 0.1. It's still right there. All right, now that second number, though, it should be 1 comma AB. And in this case, it would be 1 comma 1 times E, which is that 2.7, I don't exactly remember what it was, but about 2.7 or so. And to figure that out, if I were to plot the point, or the line, I should say, x equals 1, let's do that. X equals 1 here. What do you think this dot is going to be? It should be 1 comma E. Yeah, and that is, it's the 2.7 0.718. So that makes sense because that's true. Now we can shift this the same way that we did when it was a times b raised to the x. So let's say that I have maybe, instead of raised to the x, what if I say up here, oops, I might need to put that in parentheses. Let's say this is going to be x minus 2. Remember, what should this do? If it's minus 2, it should move it to the right 2. And there you go. All right, compared to my original, I'll put the other one back here. If I have e raised to the x, e raised to the x, here's my original. And so this should get shifted over 2 spots. So instead of being at 0, 1, it should be at 2, 1. And yeah, it is. Okay, I can't quite click exactly, but it would be right there at the point 2, 1. All right, that's if it's shifted left to right. And then what if this was also maybe, let's move it down, let's say 5. So I could put minus 5 at the end. You can see it does go down 5. So this thing compared to the original e to the x is shifted shifted right 2 and down 5. So again, this point right here was at 0, 1. So it should be over 2 and down 5. So 1, 2, 1, 2, 3, 4, 5. And it is. It's right there at the point 2, comma, negative 4. Now remember, this also originally had a horizontal asymptote of y equals 0. But because this is minus 5 at the end, this is also shifted down 5 to the line y equals negative 5. Okay, so with all that said, I'm going to go back to my notes, and we're going to graph some of these right here, and then we'll maybe even get to some story problems at the end. This says to graph the function and then state the domain and range, which are listed at the bottom. All right, just like before, I can already plot or say what the domain is on each. These, the domain is going to be from negative infinity to positive infinity. Okay, just like that. And because, right, if I think that this one, right, it'd probably be going up somehow. And every single x value will be taken. Even though it looks like it's going pretty vertical, it will eventually go all the way over to, to positive infinity. Like that. So let's see what's going on. This one, compared to just my regular y equals e to the x, it's being shifted to the right 3 and then up 2. So if you remember my 2 original dots that I have, I should have the point 0, 1 and the point 1e, which is about 2.7, along with a horizontal asymptote of, make my line really small here, a horizontal asymptote of 0. So originally it should go through those 2 points like that. Mine should be shifted, like I said, right 3 and up 2. Okay, so in red, maybe I'll do that shifting. This is going to go right 3, 1, 2, 3, and up 2. So this dot, again, 1, 2, 3, 1, 2. And this dot was at 1, comma, e, which was 2.7. 1, 2.7. So it's going to go right 3, 1, 2, 3, and then up 1, 2. So now it'll be at 1, 2, 3, 4, comma, 4.7. Okay, so, and then also you might want to think that your horizontal asymptote is also shifted up 2. So instead of being at y equals 0, now it's at the line y equals 2. And if I were to graph all this in red, it's going to go through those 2 points just like that. And the whole thing is shifted to the right 3 spots and up 2. Okay, letter B. This one does have a different number besides the 1 like we had in the previous example. This is negative 0.5, right? And that negative is going to flip it over the x-axis. So this one's actually going to be going down. Okay. And also this would be like saying negative 1/2 e to the x is my original function. And then the plus 1, this one is left 1 spot, and it's also going to be down 3. All right, so it's left 1 and down 3 compared to the original. So let me graph the original first. I think I used blue last time. I'll do that again. And originally, if this is you might want to think like a times b to the x, just like we had with our normal exponents. My a here is negative 1/2. So I need the point 0, negative 1/2. 0 and negative 1/2 will be right there, as well as 1 comma negative 1/2 times e. And you can use the calculator for that. And if you want to think, how do you type in e? So it's just e. Well, you could use that 2.71 or whatever, or you can just say like e raised to the first, and that'll be the same thing. Just like 5 to the first is 5, e raised to the first is that 2.7. So if I take that number times negative 1/2, I'm typing it in now, I get negative 1.36. So 1 comma negative 1.36 be right there-ish. And again, that would have a horizontal asymptote of 0. And so this one's going to go down. Again, it's going down because of that negative in front. However, I have to shift this left 1 and down 3. Oops, down 3. So each of these are going to go left 1 and down 3. 1, 2, 3. So that first dot's going to be here. This one's also going to go left 1 and down 1, 2, 3. And for my students, I'm just looking at this kind of in the ballpark of the right spots. Your teacher might be a little bit more picky than me if you're not one of my students. What I also am looking for, though, is the horizontal asymptote. That's also going to be down 3 compared to 0 like we originally had. So this is going to be down 1, 2, 3, just like this. All right, and then using that asymptote along with the 2 dots that I drew, we can go ahead. That's probably not the best one. We can go ahead and get close to our asymptote, hit our 2 dots, and then go down pretty quick like that. Now, again, if your teacher wants you to, plot more points along here to be more precise, you can do that. But those 2 points are where it's going to start to curve. No matter what's going on, you can always find what the original is and then shift it based off of what's going on in the exponent as well as behind the problem. Okay, now in each of these, we also needed to list out the domain and the range. And like I said earlier, the domain is going to be from negative infinity to positive infinity on both. The range is going to be in this one. Remember, it's the red line that is what the final product was. That blue one is just the original. So I'm basing my range off of the red, and here it starts at 2 on this left problem, and then it's going to go up to positive infinity. So starting at 2 goes up to infinity. This one's going to go down, all right? And so I have to start the lowest, which means I'm going to start at negative infinity, and then this one caps off at right here, which was the line y equals negative 3. So it's going to stop at negative 3. Remember, both those, whether it's the 2 on this side or the negative 3 over here, both are going to get parentheses because we never quite approach that asymptote. That's kind of what an asymptote is. You get really close to it, but you never quite touch it. All right, let's look at this next slide. This is going to be kind of the introduction to some interest problems and just kind of exponential growth and decay word problems. And you'll notice that this is the formula we had the other day, where it was a equals p times 1 plus r over n raised to the nt. I mentioned that in the beginning of this video. And that's where n is the number of times things are compounded. If you want to compound continuously, we can actually use e. And this formula is similar, but slightly different because e has to be raised to a power. And so here that e, it sort of takes the place of the n in a sense, but, and also the 1 you might say, but this is going to be a equals pert is how a lot of people remember this, P-E-R-T. A equals pert, where a is our final amount still, p is the principal or the initial amount, r of course is the rate, and t is the time. So with that in mind, I think I have that on the next slide. Oh, I don't. Let's do this one first. I'll switch the order of those two. This one says we're going to compound this continuously. So we have to compare the balance after 30 years of a $15,000 investment earning 12% interest compounded continuously to the same investment compounded quarterly. And we're going to find something out after doing this problem that's going to be true for every type of compounding that you do. And it's going to be important for our test coming up as well. So I might move this money out of the way so I have more room to write. Okay. Now let's do our original formula first, which was, I might throw that over here as well. A equals P times 1 plus R over N raised to the NT. Okay, and let's use that one first with these numbers. And it says we have a $15,000 investment. So I'm looking to find what A is. I don't know the A, but I do know this is going to be $15,000 times 1 plus, and then the R here is a rate of 12%. As a decimal, that's 0.12 over N. This is compounded quarterly this time. We'll do the continuously one with our new formula in a second. But for right now, quarterly, I'm going to plug in a 4 for the N. Okay. And then raised to the NT. Well, if it's 30 years, T is 30, and then the N is 4. 4 times 30 is 120. So we're going to find this one out. Give me a second to type this in. We have 15,000. Hopefully you're doing this with me. 15,000 times, parentheses, 1 plus 0.12 divided by 4, all raised to the 120. Okay, and this gives me 520,000. I'm in my basement right now. It's really dark because we have a snow day. And so I can't see my calculator. All right, 520,664. And then this would be 81 cents. There we go. So $520,664.81. 15,000, that's not too bad. $15,000 turned into 520,000 after 30 years. Now you got to leave it alone that whole time, but I'd probably take that. So, by the way, if you ever can find something that has a nice return, you might want to consider doing that. And then if you plug in more money each time or each year, that's going to be an even bigger number. So turn you into a millionaire really fast. Anyway, let's try the same thing with A equals PERT. Okay, so maybe take an educated guess. Do you think by compounding continuously, which is more than quarterly, is it going to give you a bigger or a smaller number? So we'll try it here. So A equals PERT. Again, I don't know the final amount. The P is that initial 15,000. Okay, then I'm going to just take it times that E, that natural number that we learned, raised to the R. Still, this is going to be, you might want to use a couple sets of parentheses here. This is going to be 0.12. And I'd open up another set of parentheses, and our time here is 30. If you want, you could multiply those together first, but I'd probably type it in that way and be very careful the way you type that in. So let's do that. Let's go 15,000, and then E raised to the, and open the parenthesis format and go 0.12, open parentheses again, 30, and I got to close both. And this gives me 548,973.52 if I round. Okay, so by compounding continuously, you made an extra about $28,000 there just by the way that it was compounded. So again, if you ever invest, you might want to just make note of how it's compounded. If you have a couple of funds or something that look pretty even, maybe the way that they compound, whether quarterly or continuously or daily or something, the more that something is compounded, the more money it will return. And that's going to be true if this was compounded quarterly and we found something else that was compounded weekly. The weekly one, since that's more often, is going to yield more money. All right, just like if it was maybe biannually, which means twice a year, versus monthly. Well, monthly is going to happen more often. So the one that happens more will get you more money. And that's going to be true no matter what type of compounding it is. All right, let's try this problem now. This is similar. This also uses E, but this is a different type of formula with some exponential, I think this is exponential decay. Yeah, it's removed from a heat source. So this one says, according to Newton, a beaker of liquid cools exponentially when removed from a source of heat. Assume that the initial temperature is 90 degrees Fahrenheit and that K equals 0.275. Find the temperature of the liquid after 4 minutes. Now, I'm going to do this one, and I'm going to start plugging in these numbers, and you're going to see something that happens. Don't want to spoil it here, but let's just try it, all right? And then I'll show you here at the end. So that's initial thing. It says N, the way you read this is N equals N naught. That's just altogether one number, times E raised to the KT. All right, so we want to look, I think we're looking to find what N is. And then our initial, that's what N naught is the initial amount, which was, I think, 90. All right, and then it's going to be E raised to the K, which here, K, it says is 0.275. And then T is the time, and that's going to be after 4 minutes, so times by 4. Again, type this into your calculator, and you're going to notice something right away, that something's off. So I'm going to do it too. This is 90 times E raised to the 0.275 times 4. Again, you might be careful with how you plug those parentheses in. And when you do this, you get 270. All right, 270.37. Why is that not right? Okay, it is not 270 that should be happening here, because if you think my initial was 90 degrees Fahrenheit, and what did I do? We removed it from a heat source. So should it be getting hotter? No, it should be cooling down. And so what did we do wrong? Well, if you remember back to the very beginning of this, in the first slide, we said at the bottom that how do we know if it's a growth or decay? Whether this is a negative number, it's going to be a decay, or a positive number, it's a growth. So in ours, our number's fine. It's just the sign that's wrong. So instead of being 0.275, it should be negative 0.275. And that negative is going to make all the difference. So instead of 270 degrees Fahrenheit, which is over boiling, if it's water or whatever, I'm going to go back into my function. Instead of 0.275, I'm going to insert a negative in there. And now when I hit enter, yeah, this makes a little bit more sense. N equals 29.958. Okay, and that's going to be in degrees Fahrenheit. So it did cool down that time because of we just switched that to be a negative. So you got to kind of read what the problem's asking, decide is the value that they're raising the E to, is that positive, is it getting bigger, or is it negative if it's a decay and getting smaller. All right, so got some notes for you today, and then I think if you're one of my students, there's going to be an assignment online.